let's take a look today at how to find the integral of functions that involve the inverse trig. Okay, for example, 1 over the square root of 1 minus x squared dx. Okay, well, let's take a look at that. There's only one function that has a derivative that looks like this. Well, that function is the inverse sine. Okay, the inverse sine. So we would say, now you may also sometimes see this written in answer keys, like in textbooks, older textbooks and things, you might see it written like this. Okay, they both mean the same thing. Okay, so then, but what happens if I put a negative 1 on top? Well, okay, well, technically, that could have two answers, just like this guy up here could have two answers, but I'll give you the main answer. The inverse cosine of x plus c, which also can be written like so, with the arc symbology. But both of these have an alternative answer, because this could be the negative inverse cosine function, and this one could be the negative inverse sine function. Okay, so those are some things you need to keep in mind. Okay, just a little food for thought as you go forward. All right, that as you think about these two antiderivatives, because of the nature of the inverse sine and cosine derivatives that are of these forms, you could get both answers for that. All right, so the same holds true for our other trig functions, our other inverse trig functions. So let's say I had the integral of 1 over 1 plus x squared. Well, the only thing that can give us that particular derivative is the inverse tangent. Or, as some people write it, the arctan. Arctan, not arctar, har har. Okay, so, but remember, this could also be the negative form of the inverse cotangent, because these are the same derivatives. All right, now for that matter, if you see the negative 1 over 1 plus x squared, that typically then would be the inverse cotangent, or the arc cotangent of x. But it also could be the negative form of the tangent, of the inverse tangent. Okay, so again, those are a couple of things you need to know. And each one of these is, you're going to have to kind of commit to memory and be able to recognize as you move forward. So let's look at the last two of these types, and then we'll just do a couple of extra examples. Let's say you had the integral of 1 over x times the square root of x squared minus 1 dx. Well, there's only one thing that gives you that derivative, because remember, this thing sitting here is a derivative, so there's only one function that gives that derivative, and that is the inverse secant, or the arc secant of x. Okay, now again, just like in previous problems, this is also the negation of the cosecant inverse. So you could count either one for this. And that's the same thing again holds true if I do the negative version of this guy. Then I would have the positive cosecant. I got to rewrite this. Sorry about that. Which is, again, could be the arc cosecant plus of x plus c. Okay. So, and it's alternate solution of the inverse secant again. And these are things you could consider as you move forward. But these 6 integrals that I just gave you, you really need to recognize their forms and be able to answer these questions. So let's look at a few examples that kind of extend this a little bit. All right, let's talk about if I had -3 over the square root of 1 minus x squared. Now this looks kind of like the inverse cosine or the inverse sine. Well, because of this 1 minus radical x in the denominator, it is one of those. But this 3 on top, well, to handle that, I just put it out in front of my answer. So I would say -3, okay, or +3, depending on which trig function you chose. I'm going to go, because it's negative, I'm going to go with the inverse cosine. And there would be my answer. Okay. But I also, again, could say -3 inverse sine of x. All right. Well, what if I then had something like 5 over 1 plus x squared dx? Well, I do it the same way. Notice this 1 plus x squared in the denominator really indicates the inverse tangent. So I would put a 5 in the inverse tangent plus c. But I also could do -5 and the inverse tangent plus c. So any of those could work. Or maybe I have 4 over x times the square root of x squared minus 1. Well, that would be, again, I would take the 4 and put it in front, and this would be the inverse secant plus c. So these are the kind of things you can look at as you move forward and see questions of this nature. All right, I want to do a couple more. And let's talk about what happens if some numbers are kind of a little odd. All right, what if we gave you something like this? Interesting, huh? Well, I forgot the dx. Okay, well, this is still an inverse trig function because you have something minus x squared in the denominator. Okay, so it doesn't match it exactly. So what we're going to have to do is do a little manipulation to do that. Okay, so what I'm going to do, you see this 4 here, I need to pull that out of the radical. Okay, now when you pull the 4 out, it's like factoring out a GCF. Okay, and that's exactly what I'm going to do. When I pull the 4 out of 4, I get 1, of course, not a 4, almost did that, I get a 1, minus, but when I pull a 4 out of the x squared, I get x squared over 4. But since I'm factoring it out, when I go outside the radical, I have to take its square root. So I end up getting 2 in the front. So now of this format. Okay, again, all I did to get to this step is I took a 4 out of both terms. All right, and that's why it looks this way. Well, that gives me 1 over 2 radical 1 minus, and what I'm going to do is I'm going to rewrite this like so. Okay, now this should be a little bit more recognizable now as the inverse sine. Okay, so when I write my answer to this, because I now can, I have the inverse sine, and this 2 actually disappears when I do this, of x over 2 plus c. Now there's a lot more that could go into this, and I could spend about 10 minutes doing a problem like this to show you extra techniques. But you just have to trust me that this 2 would disappear. The 2 sitting here disappears in the problem. Notice I don't include it in the front. Okay? Because if I were to now take the derivative of this, I would get this guy as an answer. I would go back. So again, if I took the derivative of this, take a look at what you get. Okay, it would be the derivative of that, which is 1 over 2, over the square root of 1 minus x over 2 squared, which is really 1 over 2 radical 1 minus x over 2 squared. And notice that this is the same thing as that. Okay, let me do another one of these. Let's try the integral of 1 over 9 plus x squared. Now again, this looks like a lot like a tangent function. Okay, it looks a lot like the inverse tangent. But because this is not a 1, because this term is not a 1, I have to turn it into a 1. And the only way to do that is to factor out a 9 out of both terms. Okay, so that would put a 9 in front of the parentheses, and that would be 1 plus x squared over 9. That's what you get when you factor a 9 out. Remember, when you're taking out factors like that, you're dividing each term by that factor. So this 9 here became a 1, and x squared become x squared over 9. Well then, just like in the previous question, I have to break this square up into x over 3 squared. All right? So this fits the form now of the inverse tangent. Okay, so my inverse tangent now would be the inverse tan, of x over 3 plus c. Okay, and I do have to deal with this 9 now. That would actually be a 1/3 in front. And you can verify that. Let's take the derivative of this now. Okay, 1/3 times 1 over 3, 1 plus x over 3 squared. Which when I simplify this, I get 1 over 9 times 1 plus x over 3 squared. Okay. And the reason I had to turn that into a 9 is because since I didn't take the square root here to pull the 9 out, these two, pardon me, these two numbers have to jive. So because of that, because there's a 3 here, I need to look at this in terms of 3s. And that's why I changed that to this, so it matches up. Okay, simply, I just divided by the 9 by whatever number was sitting underneath the x, and that gives me the number I want. Now again, there's a higher level of math to this that I could go to, and this is just in case you see these in random problems in the future. Once I get to my series on use substitution, this process will become a little bit more clear. All right, thank you very much.